welcome to my solution key for this assignment. Our task is to create a sketch and a polynomial functions equation that satisfies given characteristics. Before we head into it, I want to go over what a polynomial function is, what its equation looks like, and what they look like graphed. A power function is a function that contains a variable with an exponent that is any natural number, meaning it's whole and positive. For example, this is an example of a power function. A polynomial function is the sum and or difference of power functions. For example, 3x squared plus 5x. That's an example of a polynomial function. All polynomial functions have graphs with smooth and continuous curves without asymptotes. For example, this is an example of a polynomial function, whereas this is not. The equations can be in different forms, such as expanded and factored. Factored form looks like this. Seeing as they're multiplied together. And expanded form looks like this. Where they're added together. Now, the best way to get started with the problem is to break down what each characteristic really means and apply them to an ongoing graph. So for me, it's easier to kind of see the graph transform with each characteristic added. And then step 2 will be to kind of determine an equation from all the things that we've learned. And then kind of do a final graph at the end with graphing, a graphing website. So characteristic 1 tells us about the long run behavior of the function. More specifically, it's p at x must be positive when x is from negative infinity to negative 6. So, what does this mean? On the graph, it will tell us that from negative infinity, which we'll say is over here, to negative 6, it'll be positive, so above the x-axis here. So the line will come down like that to negative 6, always being positive. So this tells us half of the long run behavior. Another thing that we know about characteristic 1, what it tells us is that there's an x-intercept at negative 6. This is helpful for our equation. So we know it's going to come here. So this is helpful for our equation because we'll know that in our equation somewhere there will be an x plus 6. How do we know that it's x plus 6? Well, if x is equal to negative 6, and we're going to try and set that to 0, we do plus 6 on this side, plus 6 on this side, so x plus 6 equals 0. So since it's an x-intercept, we know that it's in a root of the equation, and this is our root for our equation. So we have to keep in mind that that will be in our equations. Characteristic 2. P at x has exactly 6 turning points. Firstly, a turning point is a local minimum or maximum on the graph. For example, this function has exactly 2 turning points. Here and here. This is a minimum and this is a maximum. Maximum meaning it's concave down, it's at the vertex of a concave down, and this minimum means it's at the vertex of a concave up. So, P at x has exactly 6 turning points. We know that it goes down to negative 6, and it has 6 turning points, so we'll just do a rough sketch of what that could look like. 1, 2, 3, 4, 5, 6. So we know that if it has 6 turning points, that the other half of the long run behavior will actually be here. So the limit of y as x approaches positive infinity is equal to negative infinity. So now we know the two ends of our long run behavior, which is really helpful when we're going to try and draw our graph, because we know that with 6 turning points, it is always going to be down here. And we'll know that if it goes up here, that it wouldn't actually have 6 turning points. Characteristic 3 is that p at x is degree 9. So what is a degree? A degree of a function in expanded form is the highest exponent in the function, and in factored form, it's the sum of all of the exponents in the function. Also gives us clarification about our long run behavior. We already know it, but this gives us secondary information so that we know that we're right. So degree 9 is an odd number, so it's an odd degree function. We know that odd degree functions have long run behavior, opposite long run behavior, and when it's positive, it's limit of y as x approaches infinity equals infinity, and the limit of y as x approaches negative infinity equals negative infinity. So like this would be an example. However, we know that our equation has the long run behavior of this, somewhat, with a bunch of turning points in the middle. So it doesn't mean that ours isn't an odd degree function. In fact, it means that ours has had a vertical reflection above the y-axis, meaning that our equation is actually negative. So this is a huge step, and we can add it to our equation up top, that this will end up being negative. Characteristic 4 is that p at x has a local maximum at 4, 0. So we already know what local maximum means, so we can kind of start to develop a more complex graph. Here's negative 6, comes down, has a bunch of turning points, and then at 4, there's a local maximum, meaning that it'll look something like that, with that being the maximum at 4, 0. So this also helps us with our equation. Since this point is on the x-axis, it means that there is an x-intercept at 4, 0. And so we know that it looks something like this. X equals 4, minus 4, minus 4. X minus 4 equals 0. So this is part of our equation. However, because this doesn't go through the x-axis like that, instead it goes down, we know that it's order 2. Order 2 means that this root would be squared to make sure that it has a turning point at the x-axis and not going straight through. So this we can add to our equation because we know that it's in there. Characteristic 5 is that p at x has a y-intercept at less than 0. It means that when it crosses the y-axis, it must be below the x-axis. So it must be anywhere here. Okay, characteristic 6 is that p at x has exactly 3 x-intercepts. So this is a very important one. We already know that our graph has 2 x-intercepts for sure, at negative 6 and at 4. So it has one more. This is important because we know that it can only, that 1 and 2, that it can cross here, but that only once. I'm gonna go with x minus 6 squared, meaning that it has a maximum at 6. I want to go on and talk about the equation to see if we can get it right. So right now, as it's written up there, our equation looks like this. Negative x plus 6, x minus 4 squared, x minus 6 squared. So right now that is our equation, and it looks pretty good. This fits the long run behavior. We have 3 roots, and most standing out to me that it could be wrong with this equation is the fact that it would not have 6 turning points, and it's not degree 9. Right now it's degree 5. We want to get it to 9. And I think that this stumps a lot of people, but the solution to making it degree 9 is very simple. The issue is we want to make this have more exponents to add to 9 without compromising our 3 x-intercepts. We can't make it more. So I was thinking, how do you add a root without adding an x-intercept? And the answer is with imaginary roots. So imaginary roots are when you set them to 0 and they're an imaginary number. So minus 3, square root. There isn't, this number would end up being plus or minus root 3i. So this makes, because it's a root of a negative number, it means it won't intercept the x-axis. It will actually be imaginary. There will be turning points in the equation, but they won't intercept the x-axis. And as well, a very, very important thing to note about imaginary imaginary roots are that there are 2. So it's plus 3i and minus 3i, meaning that this x squared plus 3 will actually create 2 roots. So we'll add x squared plus 1. So now we see that we have 1 plus 2, which is 3, plus 2 is 5, plus 2 is 7. So we're still missing a 2. However, we can make this one squared. Now we know it's a degree 9 function. But you're probably wondering, how do we know that this has 6 turning points? Well, we know that this has a turning point, right? It's a local maximum at 4, 0. So that's 1. We can keep a tally. It's 1. This one has 1. And this one has 4. So 1, 2, 3, 4. That's 6. So that's how we know that it has 6 turning points. So here we can see our equation. It is very, very difficult to see without making the scale larger. So we're going to do that. We're going to make the y-axis negative 50,000 and positive 50,000. So that helps us see it a little bit better. So we can see a turning point here, 1, 2, 3, 4, 5. So we're missing 1, but actually it's just down here very, very, very far. And it's hard to scroll down that far, but we know that 1 is there because we know our equation is right, and it also looks like it would be a turning point. As well, we know our long run behavior is correct. And now it is time to check our y-intercept to make sure that it is negative. So the way that we're going to do that is we're going to make it p at 0, meaning when x is 0, we can see that it's negative 3,456. So we know that our y-intercept is negative. So now we've done our graph and we've done our equation. So we have our answer. Thank you.